You might know that most liquids are incompressible, or at least barely compressible, which means no matter how much pressure you apply, their volume doesn't change. This can be really useful, like in hydraulic cylinders, but that lack of springiness can also lead to catastrophic failure of pipe systems. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about hydraulic transients, also known as water hammer. This video is sponsored in part by Blue Apron. More on that later. It's easy to forget how heavy water is since we hardly ever carry more than a few ounces at a time. But if you add up all the water in the pipelines of your city, or even just the pipes in your house, it makes up quite a bit of mass. And when all that water is moving through a pipe, it has quite a bit of momentum. If you suddenly stop that movement, for example by quickly closing a valve, all that momentum has nowhere to go. Since water isn't compressible or springy, it can't soften the blow. You might as well be slamming concrete into the back of the valve and the walls of your pipe. Instead of being absorbed, that sudden change in momentum creates a spike in pressure that travels as a shockwave through the pipe. Sometimes you'll even hear this shockwave as banging in your walls when you close a faucet or run the washing machine, hence the superhero-esque nickname, water hammer. Banging pipes inside your walls can sound a bit spooky, but for large diameter pipelines that can be hundreds of kilometers long, that surge in pressure from a change in momentum can cause major damage. Let's do a quick calculation. If you have a pipeline carrying water that is 1 meter in diameter and runs for 100 kilometers, a fairly average sized pipeline, the mass of water in the pipe is about 80 million kilograms. That's a lot of kilograms. In fact, it's the equivalent of about 10 freight trains. Imagine you're an operator at the end of this pipeline in charge of closing a valve. If you close it quickly, you've essentially slammed those trains into a brick wall, and the pressure spike that results from such a sudden change in momentum can rupture the pipe or cause serious damage to other parts of the system. There's actually another term for when a large spike in pressure ruptures a sealed container, a bomb. And water hammer can be equally as dangerous. So how do engineers design pipe systems to avoid this condition? Let's build a model pipeline and find out. Here's my setup. I've got about 100 feet or 30 meters of PVC pipe connected to the water on one end and a valve on the other. I also have an analog and digital gauge so we can see how the pressure changes, and a clear section of pipe in case anything exciting happens in there. I mean civil engineering exciting, not like actual exciting. Watch what happens when I close this valve. It doesn't look like much from the outside, but look at the data from the pressure gauge. The pressure spikes to over 2,000 kilopascals, or about 300 psi. That's 5 times the static water pressure. It's not enough to break the pipe, but way more than enough to break this pressure gauge. You can see why designing a pipeline or pipe network can be a little more complicated than it seems. These spikes in pressure can travel through a system in complicated ways. But we can use this simple demonstration to show a few ways that engineers mitigate the potential damage from water hammer. This is the equation for the pressure profile of a water hammer pulse. We're not going to do any calculus here, but the terms of this equation show the parameters that can be adjusted to dial back these damaging forces. And the first one is obvious. It's the speed at which the fluid is moving through the pipe. Reducing this is one of the simplest ways to reduce the effect of water hammer. Velocity is a function of the flow rate and the size of the pipe. If you're designing a pipeline, the flow rate might be fixed so you can increase the size of your pipe to reduce the velocity. A smaller pipe may be less expensive, but the flow velocity will be higher, which may cause issues with water hammer. In this case, my pipe size is fixed, but I can reduce the flow rate to limit the velocity. Each time I reduce the velocity and close the valve, the resulting spike in pressure decreases. Next, you can increase the time over which the change in momentum occurs. One common example of this is adding flywheels to pumps so they spin down more slowly rather than stopping suddenly. Another example is just to close valves more slowly. If I gently shut the valve rather than allowing it to snap shut, the pressure changes are more subtle. On large pipelines, Engineers not only design the components, but develop the requirements for operation of the equipment. This will almost always include rules for how quickly valves can be opened or closed to avoid issues with water hammer. The final parameter we can adjust is the speed of sound through the fluid, also known as wave celerity. This describes how quickly a pressure wave can propagate through the pipe. The wave celerity is an indirect measure of the elasticity of the system, and it can depend on compressibility of the fluid, the material of the pipe, and whether or not it's buried in the ground. In a very rigid system, pressure waves can reflect easily without much attenuation. I've got flexible PVC pipes sitting on the ground free to move, which is already helping reduce the magnitude of the water hammer. I can increase the flexibility even more by adding an anti-surge device. This has an air bladder that can absorb some of the shock and reduce the pressure spike even further. Anti-surge devices are very common in pipe systems, and they can be as simple as spring-loaded valves that open up if the pressure gets too high. In water distribution systems for urban areas, water towers help with surge control by allowing the free surface to move up and down, absorbing sudden changes in pressure. Plumbing is one of the under-acknowledged innovations that has made our modern society possible. But when you harness the power of water by putting it in pipes, it's easy to forget about that power altogether. Water can be as hard as concrete when confined, and if you bang two hard things together, eventually something's gonna break. If you're an engineer, your job is to make sure it's not the expensive infrastructure you designed. Part of that means being able to predict surges in pressure due to water hammer, and design systems that can mitigate any potential damage that might result. Thank you for watching, and let me know what you think. Thanks to Blue Apron for sponsoring this video. Blue Apron delivers all the fresh ingredients you need right to your doorstep in exactly the right proportions to create delicious recipes at home. We are really loving it at our house and having a lot of fun cooking these meals together, not to mention eating them. If that sounds like something you'd be interested in, the first 100 people that click the link in the description will get 3 meals free with their first order. Again, thank you for watching, and let me know what you think.